Hey everyone, just let me know if I'm audible. Firstly, thank you so much for waiting, and thank you so much for coming at such short notice. Let me know if the sound is fine and if everything else is working, if the chat is working, if I'm visible. It's going to be a fun session today. We are going to be talking about design trade-offs in large-scale distributed systems. I have basically 4 main cases that I'll be covering, so it should be fun. I'll just wait for a minute before I get a sound check confirmation. Yes, we are audible. Thank you, Sandeep. Some nice sound coming here. Okay, so today's Wednesday, right? Yeah, today's Wednesday. Wednesday is when we normally release a video. We were thinking of releasing a video with a product manager, a very senior product manager, but unfortunately that didn't happen. So we had some technical issues there also. But then we decided that let's go live today. So we'll start in 1 minute. Till then, you can call your friends. If you want to share the link, you can share. It's going to be a technical topic, a technical subject. So in case you're not probably if you have graduated, it's a good idea. If you're currently working, it's a good idea to actually go through this session. Awesome. Hey Obikoya, hi. Hey Mohammed, hi Aaron. Awesome. Okay. So there's some issue when it comes to the chat stream analytics. I can't see anything pretty much, but I'll just start. And what I'll do is I'll kind of share my screen. Go for window capture. Okay. I'm a blue robot. I got the job because of you. You are the best. Thank you. Oh my God, this is so amazing. Thank you so much for this. Is that a wolf image? But that's pretty cool. Look at that. That's a super chat right there. Thank you so much. Also, guys, if you have any testimonials or anything like that, like this is amazing. I'm a blue robot. You can email to us at contact@InterviewReady, or you can always just tell us your details. We'd love to host you. I can take a mock interview. It'll be fun. We'll get to know how you cleared your interview, and what are the kind of, let's say, challenges you faced when you were preparing, or what were the common doubts that you had. What were the thoughts on your mind, and how you overcame them. Maybe you can give us some secrets. So okay. So this is Microsoft Whiteboard. I hope my screen is still visible, and I'll just reduce the size of myself to something on the top of the screen here, and I'll just increase the size of the whiteboard so that everything is far better visible. Okay, this is great. Also, video capture goes on top of it, goes on the side. Okay. So this is what we are going to do. We are going to be actually looking at some design trade-offs today. The first one, Alan is asking, don't report it. Okay. The first one that we have is push versus pull, right? As a trade-off. So I'll just write the topic first over here. Design trade-offs. Okay. What are design trade-offs? Let me actually start with the definition. In any large-scale distributed system, or in any complex system, let's say, there are going to be trade-offs that you have to make. We are going to be focusing on engineering trade-offs that we make to meet our functional requirements. For example, you might say that the best way to store an image is a blob image. Okay, but then you might say that I want my system to be built in the cheapest way possible. So maybe a certain image, let's say file storage might be cheaper, so a distributed file storage, you go ahead with that. But if you need extremely fast read and write speeds, maybe a blob system is right for you. So it kind of depends on what your requirements are, and based on your requirements, to meet your requirements, sometimes you have to do trade-offs, okay, in design. Taking the very first example of pull versus push. If you haven't seen the Instagram video that I have on system design, right, just check it out right now. No, actually don't check it out right now, check it out after this. But it's super important when it comes to notifications. The use case is simple. A person makes a post on Instagram. Okay, this is a picture. You want to share it with all of their followers. So you want to send a notification to all of their followers. So this is, let's say, follower 1, follower 2, and follower 3. This is one way to send notifications. You push the notification from the server to the people who have installed the Instagram app. Okay, Instagram is a really good example because everyone is on their cell phone, so they'll get a push notification. The other thing that you can do is you can actually ask these users to pull the notification from the server. So every 5 seconds maybe, or every 10 seconds, these users, as long as they're connected to the app, send a request, let's say an HTTP request, and get any notifications, any new updates. The server then responds with, yes, I have some updates. Post 1 is something that you have not seen yet. Please have a look. Then this follower 2 will actually download this file from, let's say, an image bucket. Some sort of a file storage system is useful here. So let's say S3 is storing this image file, and the comments will directly come from the server. So the comments, the image ID, and so on are sent here, are sent from the server. Okay, so you're seeing blue is in push and green is in pull. I'm sorry, red is in push and blue is in pull. So pull, it means that the client is pulling information from the server. Push means server is pushing information from the server, right? You can also have a hybrid approach here. You can have, for popular celebrities, you are going to be pulling from the server, because sending those mail notifications is not a good idea. Again, you can have a look at the Instagram design to find the trade-offs here. The basic idea is, if someone like Brad Pitt makes a post, everyone wants to get the notification right now, but Instagram may not be able to send notifications to 10 million people at the same time. So they'll wait for people to come online and then show that notification. Okay. On the other hand, let's say a person who has only 50 followers, it makes sense to actually push these notifications from the server to all 50 followers and quickly notify them that this is a big deal. This is a change in their lives. It's very important. Again, looking at the hybrid approach, it might be that a person who posts a lot, you can maybe take 1 or 2 push notifications in a day. After that, you say, no, these are too many. The people are getting spammed. Even with just 10 followers, it doesn't make sense to actually send these push notifications for a less popular person also. Okay, so that's the first thing, push versus pull. That's the first trade-off. Very basic trade-off. You have probably gone through it. You have probably seen it in multiple places. You have seen it in Facebook newsfeed. You have seen it in Instagram. You have seen it in Twitter. Very, very popular, but still very, very important, especially when it comes to any kind of notifications or any kind of updates. Okay. The second one is a little more interesting. In fact, I'll wait for 1 minute because it's a basic trade-off. I'll just wait for 1 minute for your questions here. If you have any questions for pull versus push, let me know in the comments. I'm a blue robot. You have made my day, by the way. I'm feeling supercharged. SQS service, AWS basically. That's an interesting point. Well, coming back to this basic model of pull versus push, that's actually a good point, Dilip. You can have, let's say, a client. So let's say this is follower 1, and you have the server. I don't know why it came as a pentagon, but okay. The follower can pull notifications, right? That can be done. But the problem here when you pull notifications is maybe you're getting a ton of pull notifications faster than you can handle. So what you do is you build an intermediary message queue or some sort of a queue, basically a request queue, where people say that I am interested in getting an update. So these updates are noted down here, these requests are noted down here, and let's say you populate this, something has happened, maybe it's New Year, maybe something has gone viral, there's hundreds or thousands of notifications which are coming in every second. So this queue has a very high ingestion rate because it doesn't do anything, it doesn't actually process the request. So ingestion rate is very high, and you can basically say the ingestion and the exit rate is configurable for a queue because it doesn't do anything, it just stores things, stores those requests. For a server though, maybe you might have 100 requests per second. That's a very slow server, but still, let's say this is much slower than the 10,000 requests that a queue can take. So you store the requests first here, and the server in its free time picks up those requests 100 per second and clears them off. That's one model of the message queue. You can just invert this. You can also say that the server wants to send notifications, so it starts putting them in this message queue. The message queue can give you guarantees like a retry. You know, if the notification doesn't go through, please retry sending the notification. This might be an important notification. Let's say a push notification for a chat message is pretty important. And then you might have some guarantees also that you can give item potency based on message ID. Again, have a look at the Tinder system design video for this. This is actually a good point. So these two are already on the YouTube channel, Tinder system design, Instagram system design. Please have a look for push versus pull, and to some extent understanding message queues also. Okay, now I'll just go through it. Does that make sense? Cost of pushing versus pulling. It's if you push to, let's say, a huge number of users, that's going to like choke your bandwidth a little bit, so it may not be a very good idea. It's similar though. The cost of pushing is not like I mean, how many do you want to push at one point in time? If you want to send 1 million, that's not a good idea. You're probably going to hammer your server too fast. So pushing is a little more expensive, but it's also nice that it's real time. Pulling is cheaper, but it's not as real time as pushing. So yeah. Vishwajit Kumbhakar says, for something like Crick Buzz, what should we use? You don't want to push for Crick Buzz. I mean, you want to use a different kind of architecture. You can actually use, let's say, WebSockets, which is going to make events. Also in Crick Buzz, you have one score. You don't have different people making posts at random times. When, like in basketball, when some point is scored, that's an update. In cricket, when a ball is played, that's an update. So you take just one piece of data and then you store it, maybe as far close to the user as you possibly can, as close to the user as you possibly can, and then everyone can subscribe to that update. So basic idea is this: you will have a database update. Let's say a new run is scored. The server actually notes that, but the server will also have a cache which will have, let's say, the last 10 balls scores. People will be asking the score after 273 balls, 272 balls. These are users. You can serve them from the cache directly. Okay, you don't want to push these notifications much. Sometimes you might want to, you don't want a polling architecture, you want a pushing architecture, in which case you should probably do this in batch. Yeah, do it in batch. Okay, so let's say 1000 users together, so on and so forth. So what I'll do now is I'll just erase this. Okay, and then we'll move on from this push versus pull model. It's a pretty interesting topic. Mansi Pandey, how about placing some message queue like Kafka? Yes, that's a great idea. We spoke about that over here a little bit up. For quick bus, best to use WebSockets than REST. Aditya, that's a very good idea. Maintaining those many sockets, some people may say, hey, that's a real problem. If you don't need continuous, absolutely immediate responses, you can go for a REST API also, which basically never polls the database. That kind of response time is not warranted. You can cache it right in the front maybe on the edge server also, no? I think that's what they call it, yeah. Basically as close to the user as you possibly can, because everyone needs the same data. In cricket, everyone needs the same data. So replicate it across your servers. Whoever connects to whichever edge server, send them that data. Okay, Idris has, but will the queue not produce sync behavior for pushing notifications? Can you expand on that a little bit, Idris? When to use REST or message queue like Kafka to communicate between microservices? Okay, Raghu Raman, have a look at the message queue video I have on the system design playlist. It's pretty useful and it'll give you the answer. Hi Gaurav, thanks for the video. Will you cover live streaming design trade-offs in this video? We have it on InterviewReady, and we are going to be, it's basically a free preview video. So do go over there, do have a look. How do you do live streaming of, let's say a system like Hotstar or ESPN? How does that work? So that's on InterviewReady. It's on get.interviewready.io. InterviewReady.io also redirects you there. Let me just share the link so that we are on the same page. Okay. Hi Gaurav, thanks for the video. Load of commentaries via sockets. Commentary is interesting. Is it a important thing? Like one sentence makes sense. Continuous commentary may not make sense, right? Is push not the same as WebSocket? Because you are anyways going to create a persistent long TCP connection to let server push data to clients. No, not really. Push not the same as WebSocket, because, well, it depends on how you're pushing this data to clients. Yeah, you need a connection. You need to be connected to the server, which means that you're holding that connection for a long time. And long polling, one of the things you can do with long polling is you send a request and you keep waiting for a response. The moment you get a response, you send another request. So that way the TCP connection is always maintained. WebSocket is let's say better at handling this kind of a issue. It's for two-way communication. Yeah, there's basically peer-to-peer communication. Whether you want long polling or whether you just want a simple pull notification is kind of up to you. If you are logged into the app, long polling is a decent idea. If you are not logged into the app, when do you need this? Maybe you can poll at a even less frequent interval. So that would be another case of, let's say, long polling. But if you break the connection, do you want to recreate the connection? Can you maintain those many connections in the server? Let's look at that in the next trade-off. It's an interesting trade-off. Yeah, I was going to take another trade-off basically, but I'll take the next one based on this, because a lot of you have questions on this. So let's go for, yeah, second trade-off: throughput versus latency. Again, I mean, if you want to get a deep understanding of this, I have already created a video on garbage collection. This video is on Java. I'm sorry, my face is obstructing your view. Sorry for that. Garbage collection. This is on Java, but what we are going to be talking about is the concept. Right, and the videos that I have made, there are two videos on this. They explain how throughput versus latency is an issue. Okay, but of course, let's deep dive into this. What is throughput? Okay, throughput means the computer is doing the things that I have asked it to do for the allotted time. So let's say I give the computer 100 seconds and 95 seconds are spent on running the application. Okay, and 5 seconds are spent on allocating memory. So in this case, it will be 95% throughput. What does this mean? It basically means the efficiency of the computer. The more clock cycles or basically the electricity I'm spending on the computer, 5% is spent on just allocating memory and on other maintenance tasks, while 95% is spent on actually making money. So if you have your cloud service and on the cloud, if you have, let's say, throughput of 70%, then 30% of your cloud costs or your engineering costs on the server are being spent on maintenance things like allocating memory, garbage collection. You might have some background processes running for God knows what reason, but basically you might be opening and closing files, etc., etc., waiting for a request to respond, so on and so forth. So that's what throughput means. Out of the 100 seconds that your application should be working, how much of it is actually spent on the application working and how much of it is spent on background maintenance tasks. Okay, this part should be clear. The next thing is latency. Latency means that if a request comes to your server, how long does it take to respond to it? Okay, interesting. I've actually heard a story of a professor, right? He had a mathematical problem and they owned a supercomputer in the college. So what this professor did was just go to the supercomputer and take over all the cores. All the cores were being run by their application, their program. So none of the other professors could run their run their applications while this professor was hogging all the application resources, basically all the computer resources. So imagine I go to this college and I say my program will be the only program which is running, while the rest of the professors have to suffer. They can't even access Wikipedia during that time. So what ended up happening is this professor had to physically stop the other professors from using this computer, because if they would stop the process, then whatever progress he had made would be lost. Okay, so you're seeing here that throughput for this professor was 100%, right? As long as the computer is running, his program is running. But concurrency or request response time, latency, was horrible. Anyone else wants to run the request, it will take the length of this process to complete and then the response will come. Okay. Look at it in terms of your application running. If you have your app running some sort of a task, and at this point it actually accepts a request, after some time it gives a response. Even though you might have sent the request here, okay, at request equal to let's say time equal to 10, it took time equal to 30 for the request to be registered and time equal to 40 for the request to be responded to. So latency is not 10. Latency for the end user is 30. Right? This is making sense, right? What you did is you ran a particular application till it was finished. After finishing, you picked up the request and then gave a response. Maybe after picking up the request, you had another app 2 running for a while. So effective latency is 30, but actual latency is much lesser. Maybe it's not even 10, maybe it's 7 seconds. Is this making sense, guys? Do you have any doubts on the definitions of latency and throughput? Throughput is the efficiency of your computer, 100 seconds that the computer runs. How much does it run your app? How many seconds is your app running in the 100 seconds that a computer is running, and latency is the amount of time that it takes for your request to be responded to. Okay, and these are sometimes at loggerheads with each other. Okay, so let's take response time and latency. Aditya Rao, what is the difference? None. Nothing. There is no difference between response time and latency. Okay. Okay. So what's the problem? If you have an application running, let's say app 1, and you want to accept a request. Okay, I won't name it app 1 also. I'll just call it cron job 1. So it's a job which runs every 10 seconds. Maybe it goes and clears your database. Maybe it sends emails. So cron job, and your application request came in. At what point do you want to accept this request? Let's say it came in at the blue line. When do you want to actually respond to your users? Let's say this is a low priority background job. You actually want to respond to the users right now, at the time of the blue line. But there is no real way to do that. Like, okay, you read the request, the operating system said this thread is important, let's bump up its priority, and this thread which is running the cron job, please take it and put it in the waiting state. Okay, when you do that, you're seeing that some sort of work is being done by the OS. It's taking this request and starting to process it. For that, it probably needs to set up some memory on the stack. It probably needs to set up some other variables. Okay, register memory, very fast, very short, but when you do this a lot, it starts piling up. The second thing is it has to put this job in the waiting state, so that might require some work. And so the time it will take to actually do this is a thin slice, and it's called a context switch. So there's a context switch. Okay, now the request is answered in, let's say, this green line over here. You process the request, you send a response. Now again there's a blue line, because you are basically doing a context switch. You are saying that, okay, there's no request now, so let me get back to the cron job over here. And the operating system does the same thing again. Set up the stack, possibly variables have to be set up, the state has to be changed, there has to be a check, and then the cron job is picked up again. Apart from the complexity of actually allowing the cron job to be stopped at any point in time and restarted later, it might change its state. Meanwhile, like, what if this request changed the cron job state? You know, you're accessing a user's email on this cron job, the request went and updated the email. So that's one complexity. I'm just keeping that on the side for now. The cost of these context switches, right? This one, and many more are coming down the line. The requests you might be getting multiple requests, which might be making network calls. In which case you want to do context switches. You basically want to take the thread to process right now. Right? You don't want to wait on the network call also. So that will also be a context switch. The cost of these context switches basically brings down throughput. Throughput goes down, which is bad. Your efficiency is going down, but your latency also goes down, because you are handling multiple requests at the same time. It's concurrently handling requests, so your latency also goes down. Now, if you want to reduce that, if you want to say, hey, I am going to make sure that the request finishes and then and only then, you know, move ahead, your latency is going to go up, your request time is going to go up. So that's bad. That's very, very bad. But your throughput is going to go up too. So that's good. This is a trade-off, right? There's no right answer. It kind of depends on what you want to do. For example, if someone comes to you and says that I need an analytics engine and I don't care whether it gives me an answer in 2 days or 10 days, go for throughput. You don't care about latency. Response time doesn't matter, right? While if someone says I want an extremely responsive app, I want something which runs rockets, right? Anything which happens has to be responded to. Of course, this kind of architecture probably won't work for rockets, but low latency things, yeah, maybe you're going to sacrifice a little bit of throughput, but the latency is going to be low. Be careful though that you don't assign, let's say, 1 billion threads. Firstly, you won't get the memory for this kind of stuff, most likely. But let's say if you have a huge number of threads, all you're going to be doing is context switching. So your throughput is going to collapse, and your work is also going to take a lot of time, because before somebody's ready, you just knock that thread out of the way and say, hey, there's a new thread in the block, and then that gets knocked away, and the operating system just keeps taking new and new threads. So that's called thrashing. You can imagine a baby thrashing, moving nowhere, just kicking about, all context switches. Okay, so that's the second trade-off. The first one, again, guys, if you want to have a look at that, have a look at the Instagram and the Tinder design videos. Push versus pull, very, very important. The second one is throughput versus latency. Have a look at the garbage collection video, super important, really useful, and something which is used also in low-level design, which is important. Low-level design actually reminds me of something. I'll do a promotion now. You guys want to see a promotion from an engineer? You'll see how awkward it is. Okay, Mustafa Mohammed, can you repeat throughput again? Throughput is efficiency, 100 seconds that your computer is running. What's the percentage of application runtime as compared to the computer runtime? So the amount of electricity that you're spending should be spent entirely on the application. However, that's a very that's never going to happen if you have context switches and if you have any kind of background memory task to ever run, which is going to happen. Like, you're going to need to clear memory, right? So yeah, the throughput basically means the amount of time you're spending running your application in total versus the total time that you're spent running the computer. Latency is response time. That's it. Barjuk, the fan is causing noise. I think there is some static. Is this better, guys? Am I audible? I'm sorry, I sometimes move away and move forward. Not much that I can do about it, possibly. I mean, there's a lot of things which are possible, but right now, this is where we are at. Sorry for that. How does indexes look in a leaderboard system design? Nikhil, that's an interesting question. If you have a leaderboard system design, I think you can send us the details at contact@InterviewReady. Send us your design, we can either review it for you or give you comments. So yeah, send us the design that you have thought of. That'll be fun. Mutaib Shah, no, it's good, don't worry, thank you so much. Okay, so brilliant. We have two trade-offs that we have discussed. I was talking about, like, the first one is kind of usually a high-level design question. If you're sitting with your team and you're discussing trade-offs for any updates that you're sending in broadcasting or something, that's when push versus pull comes in. This might be intra-service also, or intra-service, not really, inter-service. Like, if you have a microservice architecture, one service is sending 50 notifications to the other service. One way you can reduce that is just to send one single notification containing those 50 email IDs. That's the smart way to do it. And at the very last mile, at the gateways, you actually broadcast. Okay, but I'm digressing again. This is a high-level design. This is often asked in low-level design interviews. What you're going to do? How are you going to manage between throughput and latency? And we have both kinds of videos at InterviewReady. So I think we have 3 videos on low-level design and 7 on high-level design. Not videos, actually. We have 3 designs. So each of those designs have multiple videos. You can have a look at Get Interview Ready. That's okay. Keep answering, sir. Thank you so much, Nikhil. Let's head to the next trade-off. Okay, let me see what the next trade-off I had thought of was. Yeah, should I take this one or should I take? I'll take this one. Take it. Memory versus latency. Okay, I'm a little like there's a star that I should draw here probably, but yeah, basic idea is the more memory you use, the less time it takes for you to respond to request. Why? Sometimes because you're able to process requests faster if you have more memory. There's a good question why. Like processing power and memory, you might argue, has nothing to do with each other. So the simple thing that you can think of is a cache. Right? The more memory this cache has, the more records it can keep, the less time it takes, the less frequent it is to actually go to the database and fetch a record. Right? You basically, in the ideal case of a cache, your entire database is in the cache. So you have an in-memory database. You might have heard of this. In-memory databases. Not a bad idea, right? So you have a request from a client. They get a response. And if you don't need to hit the database, then this response is extremely fast, because it's basically a memory access. If you need to hit the database, then this is going to be a slow network call. And you're going to take a response, you're going to parse it, you're probably going to do some sort of pagination, maybe, I don't know, maybe you'll apply some, an SQL query, which is fine, all of that is fine, sorry. You'll basically be parsing and unparsing your request and your response from the database. And it's just a lot of processing power also saved just by using cache. Okay. So more memory is good. What's the problem with having more memory? Can I take a petabyte cache? Yeah, the min 1000. That's a good thought. You mentioned cache there. But what's the problem with just bumping up my memory, right? My latency goes down. So that's good. I think some of you are being shy. Cost. The cost increases. You might have heard that memories become cheap, but the kind of memory that we are talking about is not secondary storage. We are actually talking about memory in the server. This is still expensive. Right? So, simple trade-off. Basic idea is that the more memory you have, the less latency it will, the more memory you have, the less time it takes for you to return a result, which means your latency reduces. Basic idea. Can you think of anything else, any other situation where a trade-off like this might come up? Sort of similar to a cache. What about a chat server? Which has a lot of socket connections here. People are connected to it. What if I increase the memory of this chat server? Make it really, really big. Does it have an effect on latency? Overhead for metadata processing. Okay, that's an interesting point. Yeah, there is going to be the more memory, or let's say the more WebSockets you have in a server, the more metadata you're going to be storing around it. So that might be a cost. Maybe there are more layers that you have to go through to actually get to the final socket that you want to send information on. Cost is one thing. Yes, cost is definitely one thing. What else? when you have a chat server and someone sends a message, okay, what actually happens? Let's say you have a WebSocket connection over here, and you have thousands of sockets, or let's say 1 million sockets. The more memory you have, the more sockets you can keep, right? So the more sockets you can keep, the faster, I mean, your response time will reduce, right? Because you will be able to keep more people and send them messages. So if this message was intended for user B from participant A, then it's going to get to them. If the memory is less, then you'll have lesser WebSockets, which means that you'll probably have to get rid of a WebSocket. Like, you don't have this connection already built, so you have to get rid of somebody's connection, this red one, and then create a blue one on top of it, and then serve this blue customer here, right? So it's very similar to caching. Higher memory, lower latency. Basic idea comes up in many places. It's not just about results, it's also about resources. Okay. Might want to look into this later. The video I'll suggest to you is the WhatsApp system design video. This is also on YouTube. It's entirely free. Do have a look. Getting back to the 3 points we have discussed till now. The first one was pull versus push architecture. Have a look at the Instagram and the Tinder design videos. We discussed how this happens, like what are the trade-offs. Then the trade-offs we discussed were around throughput versus latency. This is a pretty new trade-off. It has been slightly touched upon on the garbage collection videos that we have. So if you're just listening to this, just open them in the different tab. Right now, if you go there, then you're going to mix everything up. So garbage collection, Instagram and Tinder, and finally WhatsApp is what we have now. And now the fourth and final trade-off. But before this, if we have any questions on this, let me know. This memory versus latency, or throughput versus latency. Super important, rarely discussed for some reason. Actually, the caching thing is often discussed, but few people look at the trade-offs, which is weird. Like, I guess the caching trade-offs are very obvious. That's the reason why. Yeah, that must be it. So this one is probably pretty obvious. This one is a little less spoken about, throughput versus latency. Okay, any doubts, guys? Abhishek Anand. Maybe faster garbage collection in a small memory pool. Yeah, if you have less memory to clear and allocate, yeah, that will reduce latency. But we are looking at, like, when we are scaling, right? So when there's a lot of scale, vertical scaling, yeah, garbage collection is basically affected by that single node. Don't garbage collect across in a distributed system. Just garbage collect over there in one single node. That's a valid point. Faster garbage collection will happen in a smaller memory pool. Okay, would you please provide me with top sources to find already existing project database designs, like stock management? You should probably follow Netflix. Their engineering blog is very nice. You should probably also follow. Engineering blogs are always nice. I read a lot of them. I read Netflix, I read Swiggy, Razorpay, any engineering blog that I can get my hands on. Airbnb is fine. Google and Google, I don't think they post a lot, or maybe I don't have the link. But Facebook is something I read a lot again. Facebook actually explains the topic pretty nicely, and they also have talks. So you can have a look at, I think Scale Talks is what Facebook has. Very, very, very useful as an engineer. So have a look. Sahith Reddy, last question before we head to the system design, the fourth design trade-off. Please provide good resources which has projects implemented with. Okay, I think this is pretty similar to the other one. Yeah, have a look at the Netflix engineering blog, and in general, there's no shortcut, is what I would say. Another thing that I would, anyway, let's not get distracted. Okay, file system design. What is it? What is it? Oh yes, replication versus consensus. Okay, so just to clarify, memory versus latency, usually used in a cache, usually used in a resource crunch area. I mean, if there's a particular thing that results and resources are difficult to get, that's where you kind of have this trade-off. So keep your eye out on that. If you see that, hey, I have limited resources, I just have these many threads to hit the database. Okay, this might come up. Throughput versus latency usually happens in request response. Okay, so anytime you're seeing that you need to reduce latency of your requests, I mean of your responses, this is something which should click in your mind, right? It's a trade-off. Pull versus push, it's written over here. Notifications is usually when this happens, updates is when it happens. And finally, replication versus consensus, which is trade-off number 4, usually happens when there is some sort of data consistency, or should I say consistency is not a problem, availability problems. Okay, why would we ever have any kind of replication of data? You might have heard of the primary replica or the primary secondary architecture. There's a primary DB, and what it does is it replicates all the data in it to a secondary. Let me just improve my handwriting, it's terrible, you won't be able to read it later. So this is primary and this is secondary, and every request which comes in here to this database, okay, let's say this is log line 1, you can actually log all the requests, right? Log line 2, these are then replicated to this database, log line 1, log line 2, and so on. So sequential replication of the commands which come here, wonderful, you have an exact replica of this database. So if this database now crashes, well, you can serve requests from here, you can promote this as the primary and get a new secondary, and you're fine. You know, your data is not lost, your system is still available, meaning that people can still send requests and get responses, and people are happy. Okay, basic idea is that you can also do this in a slightly different way. Let's say you have 3 database servers. The first one stores user IDs from 1 to 50. The second one stores user IDs from 1 to 25. Third one stores it from 26 to 50. Also, the second one stores user IDs from 51 to 75, and the second one stores user IDs from, okay, actually there's too much load here, so sorry for that. Let me just repeat this. One to 25 is here, 1 to 25 is here. 25 to 50 is here, so the same load is here, but 25 to 50 is here. Okay, now we have 50 to 75 and 50 to 75 here. Does this make sense? It's basically each piece of data is replicated twice. So if you lose record number, let's say 49, 49 is between 25 and 50. So this table can answer, this database can answer, and 49 again, this database can answer. So the chance of you losing a record is low. What's the benefit? Well, if there's a tremendous amount of load on this server for some reason, then after you promoted this as a primary, let's say this server crashed, you promoted this as a primary, tremendous load falls on this and probably it crashes too. This is sort of a distributed replication strategy where the idea is, hey, if there's a tremendous amount of load here, now that load is going to be halved to this and this, because only half of it is being managed by this box and half of it is managed by this box. Okay. What if our replica has considerable lags quite often? What measures should we take in that scenario? We'll get to that also next, Rahul. So, good question. Okay, so this part is clear, right? You're basically replicating data. The other thing that you can do is you can also have consensus, where basically you have three databases, and the basic idea is, to simplify, let's say you have 1 to 75 here, 1 to 75 here, and 1 to 75 here. Okay, I'm not going for distributed replication now, no chunks of data everywhere, but this is the basic idea. Let's just take these two, 1 to 25, 2 boxes were there. Now I'm making it 1 to 75, 3 boxes. Okay, they can handle this much data, let's assume. What's going to happen is that anytime a read request comes in, the basic idea is 2 out of these 3 boxes are going to say yes, or are going to give responses, and that will be considered the final response. So let's say a read request comes for data ID 29. Let's say these are box 1, 2 and 3. Box 1 returns a response really fast. Box 3 returns the response second fastest, and box 2 is trying to return a response. But I don't care. I'm not going to take this response. I'm just going to take box number 1's response. Maybe for data record 29, the value is 7. Box 3 also returns value 7. I take this and I go ahead and I give a response. Read request fulfilled. Maybe 2 would have given a value of 8. I don't really care. It's too slow. That's one way of going about things. The second way is to look at the timestamp of these 2 records. Whoever has a larger timestamp wins. So in case there's a problem, in case contention, larger timestamp wins. Another way to handle it would be that, okay, if there is a contention, maybe 3 says 8 and 1 says 7, then we are going to wait for 2 to give a response. And when 2's response comes in, that will be the tiebreaker. If 2's response never comes, then randomly give a response. You're seeing what's happening here. Consensus does not necessarily mean that the data is accurate. It just means that the servers agree on a value. Okay, and the value is probably going to be sensible, right? If they all agree on a value of 0, when actually the right values were always 7, 7, 8, something like that, and they agree on a value of 0, that's terrible. There's no consistency in the system. But what does it tell you about the availability of the system? Nothing. Availability is really high. It always returns 0. Wonderful. Obviously that's a meaningless system, but you're getting the idea. The trade-off that we are talking about here is availability. So with replication, you can increase your availability. With distributed replication, you can increase your availability at the same extent. You're basically putting your eggs in different baskets, but your eggs can be lost. And consensus is basically servers agreeing on a particular value, not commenting on its consistency, not commenting on its correctness, just on agreement. Okay, with agreement there is going to be a decision. I mean, it's going to be a response. With a response, your system stays available. That's the basic idea. What are the trade-offs? Well, if you're going to have a consensus protocol like you saw, there is added complexity. Let's keep that aside. There's also added latency often because you're hitting multiple servers, aggregating the response and sending it back. So usually this is slower. Usually you can tweak it based on your read and write requests. If you have a lot of write requests and very few read requests, maybe you can for every write you just need 2 servers to say yes, and maybe out of 5 servers then you need a lot of reads to actually go through. Sorry, skip that. So let's say you have 5 boxes, right, and you have a lot of write requests. You're just writing to 2 boxes, any 2 boxes. So once those 2 boxes say it's a successful write, you give a success 200 OK response, right? The write went through. Now when there's a read operation, you need at least 4 servers to agree on a value. Why am I saying that? 4, because basic idea is number of write and number of read replicas should be greater than the total number of servers. Simple thing, these are the number of readers, these are the number of writers, set of writers, set of readers. There needs to be some intersection, and that will only happen, pigeonhole principle, if this is greater than n. Okay, this is for perfect consistency. You can also do with, like, you don't care that much about consistency. Yeah, sure. Okay, take these many writers, take these many readers. It's okay. It's not that big a deal, right? You might lose, you might give inconsistent data, but it might be right now on YouTube how many concurrent viewers are watching this. It's not that important for YouTube. What's really important is if you send $20, which was sent above, it has to reach the server, because otherwise they're going to make a big loss. Okay, so that's amazing. The min 1000, the weakness for sharding is finding an engineer that can implement it right. Yes, it does increase complexity. Azure Cloud Learning, he did not mention about Zookeeper, but the concept is close enough, though when it comes to replica. Also HDFC also has replication if you have on top of it. Hi Gaurav, could you review my Android app I created for preparing Azure certification? Okay, message to Tracted. Okay, yeah, Azure Cloud Learning, that's absolutely correct. Zookeeper has a distributed consensus protocol. It runs on Paxos. Right, Paxos is a distributed consensus protocol. My suggestion to you would not to read its internals. It's like reading the internals of neural networks. You are never going to be implementing it. You're just going to be using it as a library. No need to read it. There's another one which is called Raft, R-A-F-T. This has been, I think, developed by Stanford. Again, it's supposed to be much easier to implement than Paxos, but to be honest with you, it is also difficult to understand. It's comparatively much simpler to understand when it comes to Paxos, but do not have a look at this unless you are really, I don't know, crazy about algorithms or distributed consensus protocols. It's not even it's not even like this is the exciting algorithm. Wow, the tree is going from here to there. It's like, this is like, edge cases, math proof all the time. So yeah, those are some consensus protocols, algorithms rather. So the idea is that your availability can be through either of these. Replication, usually the cost is pretty much the same, slightly higher maybe, because you need a little more hardware for replication. Complexity is dramatically lower. Consensus, the amount of hardware you need is, let's say, slightly lesser, but the latency kind of goes up. So that's the basic idea, right? If you're using Zookeeper, you're basically going for this. If you're using any kind of primary, secondary, architecture, then you're kind of going for this. Cassandra actually uses replication, quorum. It's sort of like a consensus. Quorum is consensus. Cool. Just to clarify, quorum is consensus on reads and writes. It's not on leader election. Okay. Just to clarify that. Yeah. Paxos is also, I think, election algorithm. Okay. So coming back to the fourth trade-off, that's replication versus consensus. Have a look at which video should you have a look at? I have one on data consistency. Again, this is on YouTube. Okay, so starting off, and the final one that I wanted to just let you guys know about is consistency versus availability. This has been talked about a lot. You will see the idea pop up in the ones that we already talked about, so I'm not going to get into this much. There's the cap theorem which comes here. Cap theorem actually is kind of funny because no one ever says that, hey, my system is not partition tolerant. It's okay. I mean, it can go down. No one ever says that. So it's always a fight between C and A. But have a look at Martin Kleppmann's article on this consistency versus availability. It's a very interesting article. Yeah, I won't get too much into this because this has been already spoken about a lot. Maybe I can link you to some blog posts, and it is, in my personal opinion, one of the least interesting trade-offs that will be asked in a system design interview or in a team discussion. Trade-off number 5. Trade-off number 4, replication versus consensus. Which one should you choose? Depends on what you want to do. If you want to keep latency to a minimum, well, replication is fine. If you want to keep the system simple, that's also good. Replication is fine. If you want less hardware and let's say higher availability to that extent, like what if your secondary also goes down? You can't do much here. But in consensus, you can fight for a long time. So that's the trade-off: replication versus consensus. Memory versus cache, we talked about it. Memory versus latency, we talked about a cache. Throughput versus latency, we talked about garbage collection and request responses, pretty important. And finally, pull versus push, we talked about social media architectures which actually use notifications and decide on the speed of the notification based on this pull versus push. Okay, now looking at this at a high level, this is what we have. It's a massive diagram. Of course, all of this is in two places. One is the YouTube videos that you're watching right now. It's got a lot of the fundamentals. And the second one is InterviewReady. InterviewReady, now what we have done is we have also added all the fundamentals, except that the added benefit is that there's no ads on the InterviewReady website. So all the free content of YouTube, we are onboarding onto it. In fact, we have already onboarded, I think, more than 4 or 5 chapters. Monoliths, how do you convert monoliths to microservices? How do you make sure data is consistent in a distributed environment? All that is already here on InterviewReady. That's entirely free. And of course, the paid chapters, there's 10 designs, which include Gmail. There's WhatsApp calling, which is different from WhatsApp messaging. There's some fundamentals like rate limiting. There's live streaming, designing a chess engine, or actually a chess website. Yeah, chess engine is a low-level design that we'll be getting to that also. Low-level designs, let me just talk about that. There's a cache design, so machine coding, a cache, an event bus. You might have heard of Splitwise. There's a similar app that we design in low-level design. Okay. Apart from that, let me also enumerate the chapters here. We have in fundamentals we have rate limiting and the high-level design of an audio search engine, which basically teaches you to use hashes, right, in a song database. So audio search engine. Let me also open up the course just to see what's going on here. Yeah, high-level design. Oh yes, there's also something similar to Apache Airflow. I don't know if you guys have ever worked on an ETL system or a job management system, a task management system, where you have some sort of machine learning or usually some data processing that you have to do. Later on it becomes a machine learning thing. You have tons of data, you have to process that data, transform it, make a cache. I mean, not make a cache, basically transform that data and store it in your downstream services. So this is something that we are also picking up. So I don't know if I can share my screen now. Yeah. Okay, I'll just share a couple of other things, useful resources. Guys, if you have any doubts, of course, feel free to always keep posting. Okay, let me share this. Okay, right, you can see all the chapters here. Low-level design. Let me just go to quiz. Let's try one quiz. I don't know what's going to happen here. Okay, this is the split-wise quiz. Why did we use a heap instead of a balanced binary search tree here? Okay, let me see. The BST has slower insertion time compared to a heap. The BST has slower insertion time compared to a heap. No, insertion time is, I think, log n in a heap. The BST has slower polling time than a heap. No way. BST, yeah, actually it does have slower polling time than a heap. BST needs more memory. Not really. The heap is the only data structure with polling support. Not really. I don't think so. Let me see. I myself have to confirm. We continue the process of eliminating the topmost elements in both heaps till one of them is empty. What is the state of the other heap? It is also empty since the sum of balances is 0. Yeah, most likely, yeah. It may have some elements remaining which we can discard. It may have some elements remaining which will be settled by the original user. It can have remaining elements only if it is a part of a group. I think it should, both sides in a payment tracking system should be the same. So that's one thing. Product has a new requirement. Every user in a group has a role of admin or member. Users are also expected to quickly view which groups they are part of. What do you do to implement these requests? What does it mean? You have admins and members now in let's say splitwise, something like that. User also expected to quickly view which groups they are a part of. Okay, they should be able to see which groups they are a part of. What should you do to implement these requests? Okay, horizontally partition the group table on group ID. Okay, denormalize, break the groups table into two tables of group metadata and group members. Yeah, this looks like a sensible one. Yeah, add a list of groups to the user object. Nah, where this user is an admin, the rest are understood to be member roles. No, I don't like that. Change the list of users in a group table to a map of users to roles. Yeah, this is also a good option, no? Let's see. Okay, I got two right. I got the last one wrong. Okay. First two were right. Okay, not too bad. Let me see what the answers mean. BST has a slower polling time than a heap. Yeah, that is true. So I got this right. This is correct. Worst case time complexity is log n. Yeah, okay. Explanation, that is a balanced BST, by the way. So that's good. It is also 0 since the sum. Yeah, my logic here was fine. What is this? Denormalize, break into groups. Hey, I almost got this one. Okay, what is the problem? Since we want to speed up queries to view groups, I don't know, is this visible to you guys? Yeah, I think it is. Okay. Since we want to speed up queries to view groups, we can make a separate table to store information about group members and roles. Okay, you have some sort of a roles thing going for you. Okay. Process of storing redundant data to optimize query processing is called denormalization. Dude, this option is wrong. It's written denormalize, and then it's written break the table, group's table into two tables. That is not denormalize, that is normalize. So this option is only wrong. Therefore, I was right. Okay, sorry for that. I'll get this fixed. That's weird. It's good that we actually tried it out. Just totally random. Awesome. Also, guys, of course, we are actively developing this. We are actively, the content is being added to, but more than that, we are actually fixing the structure. So if you see any kind of problems, feel free to let us know. I'll give you a special discount. I'll just post it on the chat. There's a festival going on in India. It's called Holi. So this is the discount which is for the course. It gives you a pretty good discount. It's the best discount we have going on right now for the Holi festival. So in case you want to purchase the course, it's a good time. Audio search engine, like I was saying, distributed rate limiting. We have email service. You can see my hairstyle is really different here, like this. Okay, and then you have but yeah, anyway, the additional free resources on YouTube are all being added here one by one. What's this? You have machine coding. Yeah, you can see that some of these are code. Basically, I code them and then write test cases and everything. Threads, setting up fast evictions. This is actually pretty exciting. Let me see this diagrams here. Okay. You can mark them as complete, and basically your course completion percentage also goes up. And at the end of it, you get a certificate. I don't know what you're going to do with the certificate, but yeah, if you want it, sure. Cool. So, guys, this is great. I just wanted to let you know about these 4 design trade-offs and the kind of things that we do as engineers, and maybe some of the resources that you can use to get better. The other thing is I plan to actually host monthly meets for interview ready users, everyone basically. So you should go there, you can sign up, and if you like things, then do let us know. Has any of you, just asking in general, has any of you actually used the mock interview ready platform recently? We have made some tremendous changes to it. It's a free platform, right? Basic idea is that for any kind of learning, you need, for any kind of interview, you need learning, which is happening here. Okay, that's step 1. You need to know before, otherwise you won't get selected basically. So you need to learn. The second thing you need to do is practice. So this is an entirely free platform. Again, if you don't practice, then how the hell are you ever going to be sure? So it's you could clear the interview, of course, but it's best to practice, right? Here, this is just an objective thing, yes or no. Over here, it's like you get better and better at it. And finally, the third thing is actually getting hired. So that's part of the step 3. We are looking at how we can. We are actually part of it already. We are talking to companies and getting them on board. But the learning and the practice is well taken care of. So if you like to do a mock interview, please feel free to go there. And if you see anything which is exciting, do let us know. We have some interesting new features. You can actually compile your code, run your code. It's coming up in the weekend. So and what else? You can have instant interviews. Lots of good stuff. Try it out. Okay, so I just signed up for interview ready, but it seems to have some issue. Linux plus Firefox machine. Let me note that down. I'm just gonna screenshot you. And I'm just gonna. Thanks for letting me know, the min 1000. Thank you so much for the good doubts also up there. Do let us know. I think you mentioned somewhere that you had a doubt on, you were thinking about a system. Send it to us. Contact at InterviewReady. Send us your designs. We can look at some of them. If they're interesting, we'll actually feature them. We can review it possibly. I would like to review it. Yeah. Send them over. We can actually take all those designs and find the common mistakes also, and the best points about design. So that's one way. And if the design is interesting enough, let's have a mock interview. This will be fun. Anything system for storing time series data like logs? Akshat Jain, there are time series databases out there. One of them is, I think, Open Time Series Database, OTSB. Yeah. Try it out. Have a look. The algorithms are also interesting. Mohit. Okay, Akshat Jain, I'd go for Kibana or even Cassandra. Yes. Time series data like logs. Yeah, Kibana, the ELK stack, which is Elastic, Kibana, Lucene, is very popular. But if you're looking specifically for data or metrics, open source is also fine. I'll tell you what we use at InterviewReady. We use Postgres. Why? Because it's okay. It works. It's fine. We're comfortable with it. We use it. And being part of a startup, we are very, very practical. We don't pick technologies for the sake of picking technologies. What we find useful, we pick it up. Like, for example, we leverage AWS to the maximum extent that we possibly can. There might be things, of course, which are out there and we are rebuilding unnecessarily. But always, as a startup, if you need any kind of advice, leverage the resources out there. Don't try to rebuild things which Amazon is extremely good at, or on the front end, you try to make it super nice, super cool. Make it basic. Start off that way. Get more users. Get some money. Get more strength. Make it better. Get some users. Process repeats. Optimize after you actually have some data. Akshay Jain, okay, I was asked how to query in a time range T1 to T2. You know what, you can come over for the monthly meets that we have at InterviewReady. That will be a good place to ask your doubts. Lots of people have lots of doubts there. We actually had someone who recently joined Salesforce, I think. She was super smart. She was telling, the interview question she had, and all of us were trying to solve it. Gaurav Raval, oh, I made a mistake there. The L stands for log stack, is it? Could be. I'm sorry if that's a mistake. But okay, cool. Guys, thank you so much for coming. If you have any doubts, do let me know in the comments. If you like the video, please make sure to share the video. And if you want, let's say, more detailed system design videos, you know the place. I know the place. It's right here. Okay. Thank you so much for coming. Yeah. I'm a little happy also that I actually picked up this topic, and I wanted your feedback on this. Basically, design trade-offs. So we have picked it up. We have picked up 5 major design trade-offs. Final iteration, push versus pull, throughput versus latency, memory versus latency, replication versus consensus, and consistency versus availability. Right? Let's do this. Let's become the best place to discuss system design. See you. Take care. Mohammed Jarbi is asking, when will be your next live stream? Guys, if you want to make it a monthly affair, we can do that. That'll be fun. But yeah, I'll let you know. Follow us on LinkedIn. It's a little easier to post notifications beforehand over there. YouTube has this weird way of, I don't know, it's difficult to plan on YouTube for me personally. It's much easier to plan and then post on LinkedIn and other places. That's what I do. Gaurav Rubble, how could I join the monthly meetups? Right now, for the last 2 meets, we have kept it with interview ready customers. There's like we are more than 5,000, but the people who come live in every session are people who just have doubts right now. People who already have jobs may not be very interested. You never know. But yeah, it's basically for the paid customers, but we make it available to everyone. After the live stream is done, the Zoom live stream, we share it to all the people who are signed into Interview Ready. So just signing in is enough for getting the video. If you want to ask live doubts, yeah, you can purchase the course. It's worth it in itself. And of course the live streams are also amazing. We actually solve some really interesting questions. Awesome. Akshat, amazing. All the best. Don't let anyone know where you're working if you're actively interviewing. But awesome. See you guys. Take care. Have a great night. And thank you so much for coming on this Wednesday night. And I am Blue Robot. Thank you so much for your contribution. It's amazing. See you. Take care. Bye bye.